So hi everyone, today we will be seeing this problem, the unchanging or. Okay, so let's see what the problem says. So Chef was recently studying the bitwise OR operation and stumbled upon the following problem. What the problem says, let f of I be 1 or 2 or 3 dot 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 or I. So this is the function which is given to us, and we will be given an integer n. We have to find the number of distinct integers or number of distinct i's rather, where f of I is not equal to where f of I is equal to f of I minus 1. So if we see the constraint on n, it's as large as 10 to the power 9. So we can't do a big of n solution. That will prove costly. Okay, that will give a TL. So these are the samples. Like if we are given if we are given n equal to 2, then we have to go till 2. So f of 1 is 1, f of 2 is 3. So clearly f of 2 is not equal to f of 1. So there are no such pairs as required, no such required answers. So the answer is 0. Similarly, if we see for n equal to 3, then f of 3 is equal to f of 2, and so the answer is 1. Okay. So also for 4, f of 3 is equal to f of 2, so the answer is 1. Now let us go to the solution approach. Okay. So see, there is one thing to note. If we bitwise OR a number which is representable in the form of 2 to the power n minus 1 with a number which is representable in the form of 2 to the power n, then the answer will always be 2 to the power n plus 1 minus 1. How? Let's see. Let us bitwise OR 3 and 4. So 3 is representable in the form of 0, 1, 1, its binary representation. 4 is 1, 0, 0. So clearly I have to take a leading 0 here, because 2 to the power n will have how many bits? 2 to the power n will have n plus 1 bits. 2 to the power n minus 1 will have n minus 1 bits, and we have to take a leading 0 in the MSB. Excuse me. Now let's see. See, 2 to the power n minus 1 will have n set bits. For starting from the LSB, we will get n set bits, and 2 to the power n will have the n plus 1th bit as set, and all these n bits starting from the LSB will be 0. So if we try to see all the bits starting from the LSB till the nth bit, okay, for the number 2 to the power n minus 1, all of them are set, and for 2 to the power n, all of them are reset. So the result will be set, that is all the bits starting from the LSB till the nth position will be set. Okay. So and also the MSB here will also be set, because the MSB of 2 to the power n minus 1 will be 0, and for 2 to the power n it will be 1. So 1 or 0 will give 1. Okay. So what is this? 3 or 4? This is a binary representation of 7. So which is nothing but 2 to the power 2 plus 1 minus 1, that is 2 cube minus 1. So we understand how 2 to the power n minus 1 when bitwise OR with 2 to the power n is given 2 to the power n plus 1 minus 1. Okay, now let us move towards the problem. The problem says f of I is 1 or 2 or 3 up till I. Okay, bitwise OR up till I. So clearly f of 1 will be 1 or 1, which is 1. F of 2 will be 1 or 2, 0, 1 or 0, 1, 0. Okay, so or 1, 0. This will give 1, 1. This is a very basic binary calculation. You know, 0 and 0 or 1 will give 1. This 0 when bitwise OR with this 1 will give 1. This one. Okay, and this one when bitwise OR with this 0 will give 1 again. Okay. So similarly we have done in a similar way this one 1 1 or 1 1, that is 3 or 3. So from here, can you notice one thing? We can say f of I, okay, f of I is nothing but f of I minus 1, f of I minus 1 bitwise OR with I? Because see here, f of 1 is 1 or 1, f of 2 is, f of 1 is 1, okay, 1 or 1, which will give 1, f of 2 is 1 or 2, and f of 3 is 1 or 2 or 3. Now 1 or 2 is nothing but f of 2. So f of 3 is f of 2 or 3. We can interpret it like this way. Okay. So f of I is f of I minus 1 or I. Okay. Now, when we do the bitwise OR of two numbers which are of the form 2 to the power n minus 1 and 2 to the power n, we get 2 to the power n plus 1 minus 1. So when we do f of 1, which is 1 is representable in the form of 2 to the power 1 minus 1, and 2 is representable in the form of 2 to the power 1. Okay, so from this thing which we have derived soon, that 2 to the power n minus 1 or with 2 to the power n will give 2 to the power n plus 1 minus 1. So you can also see that 2 to the power 1 2 to the power 1 minus 1 or with 2 to the power 1 is giving 2 to the power 2 minus 1, which is 3. Now let me take f of 4. What I'm going to tell you will be better understood there. So f of 4 will be f of 3. So let me write it down, that will be better. So f of 4 will be f of 3 ORed with 4. Okay, now see one thing, f of 3 will contain 2 bits, okay, will contain 2 set bits starting from the LSB, and the MSB will be 0. That is, f of 3 will always be 0, 1, 1. And when you OR 4, it will consist of 3 bits, the MSB will be 1, and it will be, the rest bits will be 0. So the answer will always come out to be, will come out to be 7. Okay, nothing to think more. You can see here 2 to the power n minus 1 or 2 to the power n will give 2 to the power n plus 1 minus 1. So here it is 2 to the power 2 and this is 2 to the power 2 minus 1. So this will give 7. Now see the thing. If I do f of 4 ORed with 5, okay, that is, if I calculate f of 5, the answer will come out to be 7 only. Why? Because 5 f of 4 is 7 and 5 in its binary representation will take how many bits? 3 bits. Okay, so in its binary representation will take 3 bits. So this 3 set bits, irrespective of what, whether all these 3 bits are set, reset, or whatever it may be, the answer will be 3 set bits, that is 7. Okay, I hope I am able to be clear, because see, 1, you have here 1, so whatever it may be, 1, this LSB 1, whatever the value it may be in the second number's LSB, the result will be 1. Similarly for this one, similarly for this one. So f of 5 will be 7. Now think, will f of 6 be also 7? Yes, because f of 6 is also representable in 3-bit pattern, in 3-bit binary, and again 7 is representable in 3-bit binary, that is f of 5 is the value is 7 and is a 3-bit binary and all bits are set. So the answer will again be 7. Same goes for f of 7. F of 7 ORed with 6, f of 6 ORed with 7, which is f of 7, that is f of 7 will be f of 6 ORed with 7. So this value will again come out to be 7, because we have just now understood how f of 6 is coming out to be 7. Okay, so f of 7, which will be f of 6 or 7, will again come out to be 7 in a similar way I have explained a few seconds ago how this is coming out to be 7. Now see, again you are doing a bitwise OR of 7 and 8. Okay, that is f of 8 will be nothing but f of 7 odd with 8. F of 8 will be f of 7 odd with 8. F of 7 is 7, that is 2 to the power 3 minus 1. F of 8 is 2 to the power 3, so the answer will be 2 to the power 4 minus 1, and whose binary representation is this 4 ones. 4 ones, okay. So you think, again you go to 9, it is representable in 4 bits. 9 is 1001, 1001. So these 4 bits are already set. So whatever comes in the second number, okay, whatever comes in the second number, I mean, by the second number I mean that in f of 9, you are doing one is f of 8 and the other is this 9. Okay, so f of 8 is what? F of 8 is 11111111. So whatever comes in this position, may it be 0 or 1 in the second number, that is the LSB of the second number, may it be a 0, may it be a 1, the resulting LSB will be 1. That is, this answer, the LSB of this answer will be 1. Similarly, for this bit also, the resulting bit will be 1. For this also, for this also. If you are not able to follow this I am showing it. So for this bit also, for this bit also, for this bit also, the resulting bits, the bits in the result at these positions will be 1. This, in other words, the answer will be 1111. Okay. So what did you observe? We observed that for all the numbers whose binary representation will have the same number of bits, okay, like to be more specific, see here, f of 3 it is having 2-bit binary, okay. Now f of 4 is having 3-bit binary, so 3 or 4 it is giving 7. Now from 5, 6, 7 they will have 3-bit binary, so the answer will be 7 for all these. Similarly for 7 and 8 we got 15. So for all 9, 10, 11, 12, 13, 14, 15, okay, the answer will be 15. So we see that the answer gets deferred at 16. Here is 16, here answer gets deferred, okay. So let me mark this in red. So in 16 this answer gets deferred. At 8 the answer gets deferred. At 8 the answer gets deferred. Then we see at 4 the answer gets deferred. By deferred means the answer changes, or the result, or rather the result of the function changes. Again at 2 the result of the function changes. So can we say that at the points, or rather at those i's which are powers of 2, the value of the function keeps changing, and in all other i's which are not powers of 2, we see that the value remains the same. That is, for f of 1 it is 1, then for f of 3 it is 3, okay. So you won't understand much with this 1 and 3. Let me go to 5. See, for 5 the answer is 7, for 6 the answer is 7, for 7 the answer is 7. So for 5, 6, 7, these are not powers of 2. So for them the result of the function remains the same. That is, f of I is equal to f of I minus 1 holds for 5, okay, for 5, 6, 7. Similarly for 9, 10, 11, 12, 13, 14, 15, this will hold. And again at 16 the result changes. So instead this will take a lot of time if we try to calculate this, okay. Like at which position f of I is equal to f of I minus 1, this will take again a big often time, and we will get the TL. We want to avoid the TL, so what we do, we try to find the indices where f of I is not equal to f of I minus 1, and as explained a few minutes ago, those are the indices which are powers of 2. So let me, with this intuition, let me go to the solution, okay. So let me go towards my solution. So what I have done, I have taken this n, which is the final up to which index we have to perform that function, that is 1 or 2 or 3 dot 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 or n. I have taken a count. This C stores the count of the positions where f of I is not equal to f of I minus 1, and as I have explained, those will be the positions which are powers of 2. Okay, so once we have found out the positions where f of I is not equal to f of I minus 1, so for the remaining positions f of I will be equal to f of I minus 1. So just subtract n minus c and you will get the answer. Okay.